Welcome to This Explainer. Today, we're taking a fantastic set of foundational chemistry notes and turning them into a dynamic journey. We're going to travel all the way from microscopic ions floating in a beaker right to the essential chemical reactions happening in your own home this very second. Whether you're prepping for a big exam or you just kind of want to understand the chemical makeup of the world around you, this summary of the notes is going to give you everything you need to know. Let's get into it. Okay, here's our roadmap. We'll hit the acid-base basics, indicators and reactions, the power of pH, chemistry in everyday life, essential everyday salts, and finally, water of crystallization. Section 1, the acid-base basics. So the absolutely crucial point here is that it all comes down to ions in water. Acids, well, they act as hydrogen ion donors. They literally release H+ ions when you dissolve them in water. On the flip side, bases are substances that bump up the concentration of OH- or hydroxide ions in a solution. Oh, and a quick aside, if a base happens to be highly soluble in water, we give it a special name. We call it an alkali.
Now, knowing the definitions is great and all, but how do we actually tell these clear, colorless liquids apart on a lab bench? Well, we use chemical indicators, and the source notes provide this incredibly catchy, slightly quirky mnemonic to help you instantly remember the color shifts. It goes like this: labor, try, popcorn with mayo. Let's actually decode that. Labor stands for litmus, blue and base, red and acid. TLY is for turmeric, red and base, yellow and acid. Popcorn reminds us that phenolphthalein is pink and base and colorless and acid. And finally, Mayer gives us methyl orange, yellow and base, red and acid. Honestly, it's a brilliant little memory hack to lock in those visual changes for good. Moving right along to Section 2, indicators and reactions. Okay, safety first. When diluting a concentrated acid, you absolutely must follow the ATW rule. That stands for add acid to water. You start with the water, slowly add the acid drop by drop, and stir constantly. Why? Well, because mixing acid and water is wildly exothermic. If you do it backwards and add water to acid, it can cause a massive sudden release of heat, literally leading to a dangerous burning splash or even shattering the glass container right in front of you. No, thank you. Now, what's really fascinating here is the physical proof of a reaction. When you take an acid, let's say dilute sulfuric acid, and react it with an active metal like zinc granules, you don't just get a new compound. You get a very specific gas. Bubbles form, releasing hydrogen gas into the air. And if you bring a burning match near it, it burns with this highly distinct pop sound. That little pop is your undeniable confirmation of hydrogen. Similarly, combining an acid with a metal carbonate or a metal bicarbonate generates a totally different gas, carbon dioxide. And we can visibly prove this is happening too. We just pass the emitted gas through lime water. The carbon dioxide reacts with the calcium hydroxide in there, creating an insoluble white precipitate called calcium carbonate. Basically, it turns the entire solution completely milky white. Section 3, the power of pH. So we know how these substances react, but how do we accurately measure exactly how strong they are? Enter the pH scale. It's basically our universal ruler for measuring hydrogen ion concentration, mapping everything out from 0 to 14. A pH of exactly 7 is perfectly neutral, just like pure water. Anything below 7 is acidic, and the closer you get to 0, the higher the hydrogen ion concentration, which means a much, much stronger acid. Conversely, anything above 7 is basic, with 14 being the absolute most basic you can get. We can really see the extremes of that scale when we contrast different acids. On one hand, you have the dangerous strong acids found in the lab, like hydrochloric or sulfuric acid. These completely dissociate to give a massive concentration of H+ ions. But on the other hand, you have the helpful, weak natural acids found in your own kitchen, like lactic acid in sour milk or citric acid in lemons. Those give off a much, much lower concentration of hydrogen ions. And by using a universal indicator instead of just your basic litmus paper, we don't just get a simple yes or no on whether something is an acid or base. We actually get this beautiful rainbow spectrum. It goes from deep red for strong acids, right through green for neutral, all the way to violet for strong bases. This spectrum instantly reveals the exact nature and the specific strength of any chemical on the pH scale. Section 4, chemistry in everyday life. Let's step out of the lab entirely for a moment. Every single time you brush your teeth, you're using a basic toothpaste to neutralize the bacterial acids in your mouth, acids that cause tooth decay when your oral pH drops below 5.5. Or, say a bee stings you, it injects a painful acid, which you can quickly treat by rubbing a mild base, like baking soda, right onto the skin.
And when your stomach produces too much hydrochloric acid and gives you indigestion, you grab an antacid, which is just a mild base that neutralizes the excess acid. Our biology and our medicine constantly rely on this acid-base neutralization.
Moving to Section 5, Essential Everyday Salts.
When these acids and bases neutralize each other, they give birth to a totally new category of compounds, salts. These are the literal building blocks of our households. To understand how we manufacture essential chemicals from salt water, or brine, we use something called the chlor-alkali process. And the notes give us another fantastic little mnemonic to remember the outputs of this electrolysis. PaCl CHNA. That PAC-CHNA mnemonic tells us exactly what happens when electricity runs through the brine. The positive anode gets chlorine gas, and the cathode gets hydrogen gas and NaOH, which is sodium hydroxide, also known as caustic soda. We can also take common salt and process it further to derive baking soda. You know, that magical ingredient that releases CO2 gas when heated, making our homemade breads and cakes wonderfully spongy and soft. And finally, Section 6. Water of crystallization. This is basically water hiding in plain sight. Certain salts actually have a fixed number of water molecules locked right into their crystal structure. Take gypsum, for example, which naturally holds 2 water molecules. But if you precisely heat it to exactly 373 Kelvin, it loses some of its locked-in water. It completely transforms into a white powder holding just half a water molecule per unit. We know this famous powder as plaster of Paris, the exact stuff used worldwide by doctors to safely set and heal broken bones. As we wrap up this explainer and summarize these incredible chemistry notes, I want to leave you with a quick thought to carry into your day. You are constantly surrounded by a delicate, beautiful balance of acids, bases, and salts. From the antacids settling your stomach, to the baking powder lifting your cake, to the plaster setting a bone, what chemical reactions are you relying on today? Keep observing, keep learning, and I'll catch you in the next explainer.